Hello again, everyone, and welcome to our webinar session 4. I'm going to do only part of the introduction this time. I'm going to let Mike take over. I'll let young Mike take over. So, young Mike, would you like to continue the introduction?
Thank you, old Mike, Scottish old Mike. So welcome, yes, like Mike said, session 4. A quick introduction to us as to why we feel that we are capable of doing this presentation is because between the two of us, we have got over 70 years in the aquarium industry. So of course Mike's got a little bit more than me, just due to his age, but yeah, we have a lot of experience both from the animal husbandry side and from the life support system side. Both of us started off on the animal husbandry side and then ended off on the life support system side. So yeah.
And both of us may have made as many mistakes together as the rest of you put together. So
yeah, singly we've made plenty of mistakes,
yep.
And together we've made plenty of mistakes, and that's part of the learning curve that everybody goes through. And we still make mistakes on a daily basis, but we learn from them, and that's the important part, is learning from our mistakes and sharing the results of those learnings with others. And that's why we're here doing these webinar series. Luckily, we are in a situation where we are able to gain experience from many different fields, but we can share that at a later stage. Today, we're talking about fish systems. The biology in fish, in the filters of fish systems, the overall biology of biofilms, of nutrient removal, and oxidation applications or processes. Anything to add to that, Mike? I stumbled a bit.
Preferred biological filtration systems.
Yes.
We prefer that biological filters be purpose-built and designed to encourage and make nitrification as efficient as possible.
Yes. And the reference to session 3 there is to bounce back to actually both sessions 2 and 3. They are both vitally important when we're talking about filtration. So please review those sessions as we go along. And also, if you need to have any more information, we have got a very detailed downloads page with many different documents, from manuals to case studies. So please have a look at that. And we will be putting more videos onto our YouTube channels as we move forwards, even to the point where we're going to do some application-specific discussions, elephants, and hippos and polar bears. Yeah, so as we're moving forwards, we hope to keep this channel alive and active into the future. You want to do the quick recap?
Yep, this is a recap on session 3. We can easily go through each of these in turn. I think there's little sense in that. We'd invite you instead to go back to session 3.
Yep.
And if you haven't fully taken on board everything, go back to it again.
Yeah.
And again. It's always on the web.
That's the nice thing about YouTube.
You can consult it whenever you want.
Yeah.
But the most important thing, look after your hydraulics. Make sure that you never exceed 1.5 meters per second on the suction side of your pumps and 2 meters per second on the pressure side of your pumps.
And use variable speed drives and flow meters to determine what those flows are and to set the flows to what you require them to be, which at the end of the day is determined by your pipe work and your filters. There might be a design concept, but sometimes there might be some shortfalls. Variable speed drives are great at helping you adjust those settings perfectly.
Now, overall, we need to reduce our chemical and energy footprint.
And water use.
And water use.
Let's not forget about water use.
That starts in every system with exhibit hydraulics. Thereafter, the most important part to us is filtration and flocculation. The more you remove from your water, the less you will have to treat via other processes, and the more stable your water quality. We mustn't forget make-up water. The totally closed system virtually doesn't exist. And you need to make up for minerals lost. And in any case, you will always lose some water in backwash, and you need to make that up. So also very important. And finally, oxidation demand is governed by the efficiency of your filtration. We would like to make this quarter of this diagram as small as possible.
Yep.
Because you will use less chemicals.
Yep.
Or you will use less ozone. You will have lower risks, and your running costs will be lower.
Yeah, and that speaks back to our session number 2, where we were talking about filtration and our triangle with all of these in a layering mechanism of priorities, which is similar to this one. We just presented it slightly differently with a little bit more detail. So exhibit hydraulics, filtration are the two most important concepts that feed into the need for makeup water and oxidation demand. If you get those two right, you reduce the left-hand side.
So we'd like now to talk about the biology in a sand filter and the main problems of biofilm.
Yeah, and not only sand filters, just mechanical filtration. So you also get that with some of the other medias as well. For instance, if you're using zeolite media, you'll have big biological problems as well. So it's not only sand, but sand, I would say, is the most used around the world.
Or in a filter, even our own, that is incorrectly managed. If you don't backwash it properly, you will leave organic material in the filter, and therefore a culture will start. And that's what you want to avoid.
And that all starts here by allowing bacteria to settle on the surface. You know, we in no way can we prevent that from happening in exhibits and pipeworks and all of that, but where we come from, we can help to reduce that in the filter itself. So bacteria needs to settle onto a surface before they can start producing their slime that protects themselves, the biofilm, which grows together to form many, and that can only happen once they are on a surface. When they are free swimming, they are available to reduction or to be killed by ozone or chlorines or things like that. But as soon as they settle onto a surface, they become very tolerant against all sorts of chemical additives to try and kill them off.
Every bacteria is actually looking for a surface to settle on. It's looking for a surface that it feels comfortable on. That's a very, very important aspect, and in which they can grow and reproduce. The figure at the bottom here is very, very telling. 1 cubic meter of sand has a developed surface area of 3,000 cubic meters. That is huge.
3,000 square meters.
Sorry, square meters. That is huge.
That's a massive surface area in a small amount of sand. And that you can see there, sand being one of the most perfect substrates for bacterial colonization. You can see in a very short space of time, each grain of sand is fouled by bacteria, or settled by bacteria, and then producing the slime to protect themselves from any chemical attack. If we're looking in fish systems particularly, then we're looking at how resistant they are to residual oxidants if you're using ozone in a system, and they become very resistant to any form of chemical attack.
Now, biofilm will compromise the efficiency of mechanical filtration in any media filter. So the bacteria are looking for a surface to settle on. They then settle on the grains of sand media. They protect themselves with a biofilm. That biofilm, they then reproduce within that protective environment. And they cause clogging of the sand grains. That clogging of the sand grains creates localized resistances within the filter bed, and therefore the water takes the easiest bath and it winds its way through the free bits of bacteria. It causes channeling, so higher velocity in those areas, poorer quality filtration, and also in some cases it can actually open up the filter bed and allow some bacteria to pass straight through and into the processed water.
So with the resultant effect that you have an increase in turbidity in your systems, in the outlet water, your oxidation demand increases because you have this generation of biological flocks that add to your the oxidation demand in your system, and your filter ends up being, your filtration is compromised at the end of the day, because you have no control of what is going in and out of your filter. In areas where there's clumping and a reduction of oxygen and pH, it's the perfect breeding site for pathogens. And these then, when the sand opens up into these channels, these are then released into the filtrate water, which is the clean water going back to your system.
So the filter can in fact become a culture vessel.
Yep.
It ends up producing bacteria that are released into your processed water.
Yeah, and there you can see on the right-hand side a picture where your bacteria have colonized the surface. They are starting to biofoul that surface and clumping together. This is quite often seen with the increase in pressure losses, a very fast increase in pressure losses, and never being able to bring those pressure losses back down to its original. That means that your sand has started to clump together, and the only time where your pressures do sometimes drop is when the channeling happens, and that's very inconsistent because it can happen at any time of the day. The channels can open up and then they can collapse again. So we have got a lot of reference data from studies done in drinking water, where you can see on the graph and the turbidity on the outlet of the filters where these channels have opened up for a short space of time, collapsed again, but in that process they've released all the gunk that was caught up in the filters. So we do not want biofilms in a filter. That's the bottom line, is because if you don't have biofilms, you won't have the clumping effect that you get from the biofilms, therefore no channeling, and therefore you end up with reliable filtration.
Now, any bacterial metabolism in the filter will consume oxygen as the water passes through the filter. Now, conventional logic in many aquaria would suggest that the sand filter can also be a biological filter, but the biology within that filter is not controlled.
Yep.
And that's simply because nitrification is an aerobic process. We'll explore a little bit more of this as this presentation goes on.
In more detail. So, yeah, and as this slide shows you, as your water is flowing through the media, the oxygen is being consumed by the bacteria in the upper levels. So as your water flows down, your oxygen drops, and with the result that your pH also drops. And more often than not, in filters with lateral systems, all of the media below those laterals are not being irrigated in any way, either during filtration or backwash, and they become anoxic and are a continuous source of a reduction of water quality in your systems.
So the ORP reduces as the water passes through the filter, as the oxygen levels decrease. Your requirement for pH correction increases because acidification follows the metabolism that happens in the filter.
Yep.
And the anaerobic zone that forms at the bottom of the filter, which is non-irrigated media, becomes a perfect breeding ground for pathogens, and their oxidation demand increases, and in effect that becomes a haven for those nasty bacteria that you don't want, the heterotrophs.
Yep, exactly. And also where everything else is breeding. So again, if we jump back to no biofilm, we have very little reduction of oxygen. There will always be reduction of oxygen because we cannot stop bacteria from settling on the dirt that we've caught in the filter, so that you will still have some, and there will be reduced reduction of pH, far more stable redox potential, and no anaerobic bacteria colonizing the filters. Okay. So that's the aim of a good filter. Being able to capture as much dirt as possible without clumping, and then being able to release that dirt during the backwash process and anything that's caught on that dirt.
Sure, and release that dirt regularly enough
Yeah.
before the organic material starts to putrefy, before it starts exerting an oxidation demand
Yep.
on the rest of your system, and before it starts influencing and adversely influencing your water
Your
quality.
water quality.
Now, these next slides, just put some numbers to that.
Yeah.
We said that sand has a huge surface area. On you go, Mike. Let's
Yeah, so
quantify
if we put that into a 300 cubic meter aquarium with the volume of 300 cubic meters or 80,000 gallons estimated, with the turnover of around about 3 hours, then we're looking at 2 filters that are required at 1.6 meter diameter. If we relate that into surface or media that's required in that filter, that's 5 cubic meters of media times by the 3,000 square meters, gives you a surface area of 15,000 square meters that can be colonized by bacteria. That is in the filter alone. If we then take that and to the next step and add, so on the left-hand side is what's in your filter, and then on the right we added some estimation of surface area coverage from gravel in your tank with a certain depth, theming, and then we've added all of that together. You get about 125,000 square feet or 11,000 square meters of surface area available for colonization. Compare that, and then down with your sand media, 15,000 square meters of surface area. So within your sand filter, you actually got far more surface area than in your whole exhibit itself.
Oh, those two figures are not far from one another, actually. What it says is that you actually already have quite a substantial surface area available in the tank.
Yeah.
If the water is kept moving around that, if they're kept aerobic,
Yep.
then that actually can do as much good as this apparently available surface area in your filters.
Exactly. So, and that's the bigger point, is that this surface area in your exhibit is what's being that it's been well irrigated with water and oxygen continuously, maybe not so much in the gravel depending on the thickness of your gravel, but for most of the rest of it you've got water flowing over it all the time. You've got good bacterial growth, aerated bacterial growth, which is helping with your nitrification processes. We will go into detail about the nitrification processes coming up next,
Yep.
right?
What is biological filtration?
What is biological filtration? That's correct.
So the products of metabolism, you're producing ammonia, which you need to metabolize by nitrification to nitrite and then to nitrates. Ammonia is toxic, nitrite is toxic, nitrates are less toxic.
Yeah.
But you all know this. So
Yeah, you all know this. The important part of that is each of these steps requires oxygen.
yes, it is an aerobic process. It needs oxygen, and it is very oxygen hungry.
Yeah.
Unless we keep it fed with oxygen, it cannot be efficient, and we'll get the wrong kind of bacteria developing instead of having a managed population of healthy nitrifying bacteria.
And which, yeah, so it leads to a reduction of the aerobic process, like Mike was saying, and encouraging an anaerobic process, which quite often is a longer process, but it also comes with the negative implications of pH reduction and DO reduction, increased parasites, and stress on your animals.
Yes.
Actually,
And people might think that because there's lots of water passing through your filter, that it's well irrigated, but also because of the density of that surface area, the density of bacteria can be huge. The oxygen demand is much greater than the water can supply, and therefore anaerobia in the filter is inevitable.
Yes. with sand media that's well colonized or media that's well colonized by bacteria is where we're coming from at the end of the day. This is where it should happen.
Yep.
Correct?
These are purpose-built,
Yep.
designed, biological filters that are designed for efficient nitrification.
Nitrification. It's not a media trap and then converting particles into ammonia before it's converted into nitrites and nitrates. It is really focusing on the reduction of ammonia through the nitrification process. So the implications of that is that it's far more efficient and consistent with regards to nitrification than any sand filter could ever be, because a sand filter is uncontrollable in terms of this process of nitrification.
So a trickling filter is designed to have water raining through it.
Yep.
It will have a thin film of water and bacteria on the available surface areas of the plastic media within that trickling filter. They will also ensure a very large open area for oxygen exchange, and therefore nitrification is not compromised. They're very, very good. On the right-hand side of the image, the video that was rolling there is fluidized bed biofilters. Again, we ensure good contact with air by ensuring complete fluidization of that media. Occasionally assisted by air. And that makes sure that, again, nitrification happens efficiently and that only healthy nitrifying bacteria can live in that filter.
So the bottom line is, when you're trying to do nitrification, use the right tool for the application.
Absolutely.
Right, which is biofiltration. That's why it's called biofiltration.
Select the right biomedia for the kind of biofilter that you're using.
Yes.
For example, in trickling filters in aquaculture, if the filter is too dense, if they don't have enough open area, then again, they can go anaerobic, they can become gunged up, and they don't work. The fluidized bed biofilters are far better suited to aquaculture environments or to heavily loaded
environments. That's correct.
But static, submerged sand media should not be used. There just is not enough flow to feed the oxygen that's required for efficient nitrification.
Which speaks back to the previous slide with the reduction of oxygen going through the sand filter. And this is a quick recap because it is so important and can be seen quite clearly. You've seen this picture before where the media is totally bound together by biological film and dirt in the media. So it creates poor circulation through that media, which means not all areas are well irrigated from an oxygen perspective, and therefore the nitrification process cannot happen efficiently at all.
And even with light loads, if the backwash doesn't really scrub these grains, doesn't totally fluidize them, then you will eventually see exactly the same image that you see on the right.
So we go back to backwash is vital.
Backwash is vital.
Backwash performance is vital. We have repeated that, and we will continue to repeat that, and we will continue to repeat that. For some reason this has jumped back in again. That's correct. This is talking about the ongoing biological accumulation of the biofouling with many parasites clumping onto the media, creating this consistent biofoul over the surface of all of your media, and particular on the at the top. So initially it's good because it starts to help in filtration performance, but once that biological fouling becomes saturated throughout your whole media, it is very negative and results in all of the previous clumping problems that we've been discussing, reduction of pH and reduction of DO, and creating anaerobic environments.
And despite the forced flow of water through a sand filter, it is just not enough to feed the oxygen demand of nitrifying bacteria, it's better that that happens somewhere else.
And more often than not, when this starts to happen in your filter, your water is taking the preferred easiest route, which more is down the side of your filter. And we've seen that plenty of times too. But with this heavy load in the filter, like you're seeing on the slide, we start to see other implications in your system. And that's where we start talking about ozone and the increase in the requirement for ozone, because your ORP is reduced continuously by this metabolism of the organics in your system that's not being ejected out of the system. So your ozone consumption goes up, your ORP goes lower, and you keep trying to compensate for each other, because your urine and feces and your food input stays the same, right? But everything else is going out of balance.
So urine and feces, they're obviously what's going into your system. Chemically, they can be considered as all the chemical components
you see at the bottom of the page.
You see at the bottom of the page.
Yeah.
And those will, if you don't crop them out regularly and flush them to waste, they will accumulate in your system.
Yeah.
And ORP is a measure of the balance between oxidizing and reducing agents.
Yep.
All the items that you see on this slide are reducing agents.
Yep.
And they will depress your ORP. If we can continually crop them out, and the more efficiently we can crop them out and get them out of the system, the higher our ORP will be. And that's even
stable.
If we don't use ozone.
Yeah.
So basically that means the less ozone we will need.
Yeah.
And ultimately, we can actually keep a system clean. In many cases, with no ozone whatsoever, we can actually make the ORP go up.
Or on the other side of that, your ozone might only kick in during feeding events,
yes.
right? When it's needed, rather than operating all the time, 24 hours a day. So it's a massive savings in terms of ozone generators and input of that, maintenance ozone generators, but more importantly, coming to the next point, and particularly in saltwater systems, where you end up producing bromamines through the application of ozone, the residual oxidants, so let's put that into the bigger picture of just all residual oxidants that are being created by ozone input, it can be very negative on the animals in the system. Yeah. Either you're going to generate gill burn, problems with skin lesions.
No, I think we should just qualify this slide though, because
of course.
Ozone is ozone which, if it's used correctly as a flocculating agent, then it can have very positive benefits. And if a protein skimmer is managed correctly, then ozone is only managed correctly with the correct set point for
control
ORP,
mechanism.
Then it is only being used as a flocculating agent, and it will help remove dissolved organics. Dissolved organics we can't remove in a particulate
media
filter. We can only remove them using ozone. The protein skimmer is actually a very good way. There are other ways, but ozone in fish systems,
the most
ozone the protein skimmer is the
way.
most efficient and most economical. But using contact towers, heavy doses of ozone, using ozone as a sterilizing agent, risks excessive dosage. And it risks the production of total residual oxidants, such as bromamines, which are fatal.
So by avoiding the excess load of organics in your system, you help to reduce the ozone or oxidation demand, which means your ozone usage is dropped dramatically. But I do fully agree with Mike in terms of ozone can, when well applied, is a very useful tool in all applications in aquariums.
And all this speaks back to correct dimensioning of your system. Make sure that your filtration is as efficient as it possibly can be, and then your ozone, your oxidation demand will reduce, and your system will be much more balanced. You won't need to pump in ozone to recover from a problem that didn't need to exist in the first place.
Which speaks to this. Prevention is better than cure, right?
Absolutely. Absolutely.
We believe very strongly in prevention is better than cure. Rather solve your problems at the source than trying to manage them at a later stage with chemical additions, whether that's ozone or chlorine in marine mammal systems. But the better your water movement, the better your control of anaerobia, the lower your oxidation potential, the higher your natural ORP is. It stays naturally high, the less reliant you are on ozone applications.
There are obviously events which push that.
Yeah, of course.
Feeding.
Yeah, feeding events.
And if you've got a protein skimmer, it's one of the few automated parts of your system.
Yep.
It will measure a reduction in ORP and it will respond.
Which is the way it should be. So, another repetition of organic filtration control as a safer way of moving it. But there you see what we've done there is included our key performers. Better organic filtration and better organic removal through efficient and effective backwash leads to lower levels of organics in the system, lower oxidation demand, which with the resultant higher or stable ORP and less reliance on ozone again.
Absolutely.
Yeah. Step for step, it's your best way of doing it. Prevention is better than cure. Well, thank you for joining us on that one. It was detailed in a way, and there's a lot of additional information in the background of that. So please, we are always available for questions, for clarifications, to help you assess your systems if you require. And we will provide you with our contact details on our emails. But just to prepare you for session number 5, which is the chlorinated system. So we've now done the fish systems, and now we're going to do a similar aspect with regards to how it affects mammal systems, whether they're penguins or sea lions or seals or dolphins, whatever it is. We're going to go through the same process. A little bit of a spoiler alert, because filtration plays such a big part of that process. We are going to repeat that biology in the sand filters as we discuss the biofilm creations, but then we're going to also talk more about chlorine and what chlorine does in a mammal or bird system, because it's vitally important for those animals in that system, with the gases that are being released affecting the health of those animals. So please join us for that session, and we look forward to seeing you there.
Absolutely. We're always open to your questions. Keep hitting us with them. A lot of this may seem a little bit like in search of the Holy Grail, but the more you move towards that, better hydraulics, better water movement, better filtration, the better results you get.
And if you aren't searching for something better, you're not learning to do things better. So please join us in that search for a more and improved and efficient system. Thank you very much.
Thank you all. We'll look forward to seeing you in the next webinar.